Thank you. Thank you, Martin, for the very kind introduction and for the invitation. So the talk indeed will be about tensors. What else? Conceptual and computational advances. For those of you who don't know anything about tensors, one of the most important tensor decompositions that play a role in many applications is the canonical polyadic decomposition, as I show here. It's clearly an analog of what happens with matrices, a decomposition of a tensor in a number of rank 1 terms. That will be an important thing all through the talk. Before I can explain what exactly it is and what it is useful for, let me explain a few basic things in a very short. Rank 1 terms. Okay, rank 1 terms. This is a third order rank 1 term. What is it? Obviously, it's the outer product of 3 vectors. And what does that mean? Well, nothing else but the following. At position I, j, k, you will have the product of the 3 corresponding entries of these 3 vectors. So very simple. Same thing as in the matrix case, and you have a rank 1 matrix, and the entry at position ij is the product of the corresponding entries. So, so far it's simple. What's the rank of a tensor? Well, the rank of a matrix, one way to define it, or several ways to define it, but one way to define it is the minimal number of rank 1 matrices that you need to construct that given matrix. So you can do the same thing for tensors. The rank of a tensor is the minimal number of rank 1 terms that you need to build that tensor. So you see, tensor algebra is not very difficult. At least not, the definition is not difficult. The mathematical properties of tensor decompositions and matrix decompositions are very different. You should not be afraid. This is just something to show that even very basic stuff has totally different properties. But nevertheless, it's convenient to work with. For instance, you have, for matrices, if you have now a square matrix, the rank is, of course, at most k, at most the dimension of the matrix. For tensors, that is not true. The number of rank 1 terms that you need for a k by k by k tensor can be greater than k. It's already strange. It's actually not strange when you think about it. If you have this tensor, k by k by k, here you have a number of rank 1 terms. Assume that you have at most k terms. Then you simply do not have enough parameters on the right-hand side of this equation to describe the k to the power 3 entries in the tensor. So obviously, in general, the general rank of the tensor will actually be larger than k. And that's interesting. Why is that interesting? Well, we are going to use this, for instance, for signal separation. And the terms here are going to be interpreted, for instance, in terms of signal transmitted by different users and so on. So from the beginning, you see that in tensor algebra, there are things that will allow you to handle more users than the dimension of whatever it is that you are analyzing, dimension of the tensor. So more users than number of the antennas, etc., etc. Okay, these were the basics. It was so far simple. And I promised in the abstract to discuss some conceptual advances. And one of the things that I thought I should mention is uniqueness of this decomposition, canonical polyadic decomposition. So again, this is decomposition of a tensor in a minimal number of rank 1 terms. In the setting of signal separation, these terms would be interpreted as distinct contributions to your data set. So this is the classical matrix formulation of the problem. You have a data matrix, A, and you want to decompose it, sum of rank 1 matrices, let's say. These rank 1 terms are the different contributions to the data set. They are, for instance, here in G, you have, for instance, sources and source signals, and the F vectors are then mixing vectors, or you can say that here there are latent variables which have a loading across the different channels or whatever. So what we want to do is, given this matrix, we want to find this decomposition, and of course we hope that the rank 1 terms can be interpreted. Now this expansion in rank 1 terms, if you stack all the F vectors in a matrix F and you stack all the G rows in the rows of G transpose, that is just F times G transpose. So we all immediately see the problem. This decomposition is by no means unique. You can plug in any non-singular M here and its inverse there, and there you get two new matrices, F tilde and J tilde, and you will get a new decomposition in rank 1 terms. So there is no way that you can say this one is better than the other. They are just equivalent. They yield exactly the same fit. And so that's a very fundamental limitation of matrix algebra. So basically we are saying that if this is what we want to do, we cannot solve it by matrices. But then you might say, but we do SVD all the time, singular value decomposition. It's a decomposition in rank 1 terms, and we thought SVD is unique, right? Yes, it is unique if the singular values are distinct. Now, what happens in SVD? If we go back here, so you have here coefficients. These are the singular values, just non-negative values. And now these vectors are the left singular vectors, and these vectors are the right singular vectors. What makes SVD unique is that all these vectors are mutually orthogonal, and all these vectors are also mutually orthogonal. So if you would like to use SVD for signal separation, then you will be looking for components in your data that have this remarkable property that they are rank 1 to begin with, and that all these vectors are orthogonal and all these vectors are orthogonal too. And it's a bit strange if you're analyzing images or whatever, that you're looking for components that have that property. It's of course nice, SVD is good if you want to have a best low rank approximation, but for signal separation it's of limited use. And then we go back to canonical polyadic decomposition. The nice thing is that decomposition of a tensor in rank 1 terms is very easily unique. It's unique under very, very mild conditions that have nothing to do with orthogonality nor with any of the other constraints that make matrix decompositions unique, like triangularity and QR factorization, or matrix and its inverse in an eigenvalue decomposition. You don't need that. It's just the structure as it is. Sum of rank 1 terms, it's minimal, and under mild conditions, this is unique. Mild essentially meaning that, of course, they have to be different and they cannot be the same, otherwise you cannot separate them. So the mild conditions have to do with sufficiently different and not too many. So there you see that, for instance, for signal separation, for many other things too, For instance, for signal separation, working in the tensor setting is really interesting. Conceptually, there is stuff there that you can do that you cannot do with matrices. Okay, so these uniqueness properties. This here is people working on using CPD for signal separation. This is the paper that most of them know. It's a very famous result on uniqueness of CPD, and it works as follows. You stack all these A vectors in a matrix A, B vectors in a matrix B, C vectors in a matrix C. You have 3 matrices. And you compute their K ranks. What is a K rank? Well, a rank is, of course, a rank is R when there is a set of R columns that is independent, and R is the maximum. K rank is a variant. It's the maximum value K such that every set of K columns is linearly independent. People working in compressed sensing recognize this as Spark. In fact, Spark is K plus 1. And so Kruskal, the story is canonical polyadic decomposition existed in mathematics from 1927. And it was not used. And in 1970, it was introduced by people independently in psychometrics and in linguistics who saw the potential for data analysis. And 7 years later, Joseph Kruskal, a mathematician, came up with this result, and his colleagues were very enthusiastic, and they named this K-value K-rank after him to honor the result. The result is not easy to derive. So that's it. And so you take the 3 K ranks. If the number of terms R is bounded as shown here, then the number of terms is minimal. The polyadic decomposition is a canonical polyadic decomposition because it's minimal, and it is unique. And so generically, if you just take, let's say, loosely speaking, random parameters in random values for the parameters in the decomposition, then these K ranks and ranks are just bounded by the dimensions, and you see that you have uniqueness with R bounded like this, in a linear way bounded by the dimensions, and you see R can actually, you can have a value R that is larger than any of the dimensions and still have uniqueness. Okay, so there are conceptual advances. This is a variant of that result. Let us replace 2 of the K ranks by a rank, and rank is less restrictive. K rank is bounded by rank. If at least 2 of these conditions hold, then also the number of terms is minimal and the CPD is unique. This is something else. This is the toughest part of the talk. In many applications with matrices and tensors, you often have one dimension that is long. Samples in time, samples from a population, samples, long dimension. So if you then look, let's say for instance the C mode is that long dimension. You have a tall matrix C. It's in those applications often natural to assume that this C matrix here has full column rank and the long vectors are just linearly independent. Okay. What we do now, we assume that this matrix has full column rank. We have 2 other matrices A and B, and we compute all 2 by 2 determinants of A. We compute the 2 by 2 determinants of B, and we multiply them in a systematic manner to obtain a large matrix U that has these dimensions. If C has full column rank and this matrix U also has full column rank, then the CPD is unique. And what is nice, I'm going to explain why this is interesting. The proof of this is constructive, and it tells you that if these conditions are satisfied, then this complicated decomposition of tensors can actually be computed by means of elementary linear algebra, sets of linear equations, and at the very end, an eigenvalue decomposition. To give a feeling of what the condition means, so C is a tall matrix, linearly independent vectors. That means that its dimensions are k times r. In general, we have k should be larger than r. That's one condition. The condition on the on the U matrix essentially is that it has to have linearly independent columns, and that can also be translated in a dimensionality thing generically. So we have R bounded by one dimension, and for the rest, R squared, roughly bounded by I squared times J squared. So here the condition becomes R bounded by I times J. And in Kruskal we had I plus J. So this is much better. But the condition is you need to have a long mode, sample mode for instance, but it's nice. It's, in this sense, it's more restrictive than Kruskal. In this sense, it's an order of magnitude more relaxed than Kruskal. And you can do the computation. It just leads to an eigenvalue decomposition. So these are results that have been developed in the last years. And actually, now we have intensified our study of uniqueness, and we understood the following. This is really interesting, but that's the restrictive thing. You need to have one long mode. Assume that C does not have rank R, but rank R minus 1. Does it still work? No, it doesn't work anymore. On the other hand, Kruskal is completely general, but Kruskal is linear, and here you have something that is quadratic. So what we have been doing is we have been working from this condition towards Kruskal, going from k minus 1, k minus 2, and so on, all the way to Kruskal. And we have developed a unifying theory for uniqueness that bridges all the cases in between, going from the original to Kruskal, and in both directions actually a little bit further than the original. We have the theory of the uniqueness, and all the results admit a constructive interpretation. So in all these cases, at the end, there is just an eigenvalue decomposition. So this includes, so we have a constructive proof for computing the canonical polyadic decomposition under Kruskal's condition and beyond. So we're quite happy with that, obviously. There are, besides uniqueness, there are also other conceptual advances that more have to do with the type of decompositions. This is CPD. One way to see it is that you have here a set of data matrices, and the first data matrix is just this rank 1 matrix times a coefficient plus this rank 1 matrix times a coefficient, and the whole series. The second slice is the same rank 1 matrix but with another coefficient, and so on. Same rank 1 matrix with another coefficient. So you see, you are jointly expanding a set of data matrices as linear combinations of the same unknown rank 1 matrices. Now you can say, in fact, that's restrictive. Let's expand all these matrices as linear combinations of low-rank matrices. That makes sense. Why does that make sense? Well, this rank 1 structure here It's something that we always do, and we think in terms of rank 1 matrices, but that means that in our data, we are going to look for meaningful components that have the remarkable structure that if you isolate them, and you see, this is, for instance, epileptic behavior in electroencephalogram. The remarkable structure is that all columns are proportional, all rows are proportional, and all Mo3 fibers are also proportional, and that's then epileptic behavior. That is probably oversimplifying things, but if it's a good approximation, it will work in many cases, but this might be more accurate. Low-rank matrices and linear combinations. And the nice thing is, this is something that you can do in the tensor setting. This is also unique under mild conditions. And you can further generalize because now you have a term here, but still all these vectors are proportional. You can say that you look at terms that are such that they are just generate activity that is low dimensional in all modes, and this is still unique under mild conditions. I was quite happy when I found this. So one analog is with, I'm exaggerating, but it's nice to see what is going on here. You can see that a rank 1 term, in fact, is an atom of data. It's a constituent element, and everything can be reduced to rank 1 terms, and you cannot reduce it further. Now, not always splitting in atoms is conceptually the thing that you want to do. Maybe you want to split in molecules that have a meaning. And this is a molecule. It consists of rank 1 terms, but it has another level of interpretation by itself. And you can do that with tensors, but not with matrices. For instance, a molecule could be sound, not just one frequency, but sound. Okay. So far, I haven't said anything about constraints. You don't need them for uniqueness, but you can impose them if you think it will facilitate interpretation. It can even give better uniqueness results, improve the accuracy, and so on. So you can impose constraints if you want. And something else, so we are now moving from just one matrix decomposition to one tensor decomposition to several matrices and tensors that are coupled and that have stuff in common. For instance, in recommender systems, you could say we have a number of restaurants that receive scores from different users, people, on a number of criteria, and you have a data tensor that you want to analyze, but in addition to that, you have maybe a matrix with user similarity, or maybe some other matrix with how close the different restaurants are, and so on. And so maybe there are things that these data have in common, and this may facilitate the interpretation or add stuff and so on. So coupled in some way. Maybe you have an A matrix that appears here and also there, or maybe this A matrix is generated by some variables, and here you have a different matrix, but it's generated by the same variables, or some variables are shared, and so on. Coupled matrix tensor decompositions. We have been studying uniqueness. In many cases, this just leads to an eigenvalue decomposition. We can impose structure like orthogonality, non-negativity, constant modulus, rational tuplets, Hankel, and so on. And it's interesting for data fusion. So another application is, for instance, in a medical thing. For instance, you take an EEG recording, and here you have the result of a scanner images, and they are coupled in some way, and you want to analyze that. Okay, so These were the conceptual advances. I also promised some computational advances, and for that I'm changing the looks of the presentation. I've taken a few slides that were prepared by Laurent Sorber, and Laurent Sorber is co-supervised by myself and colleague Mark van Barel from the computer science department. We have been developing numerical algorithms optimization based for the computation of tensor decompositions, and we have developed a MATLAB toolbox. We have actually developed 2 MATLAB toolboxes. And this is the second part of my talk. Tensors are in fact multilinear, they are polynomial in fact, and they are between linear and nonlinear. Linear is, we understand linear completely, but it's limited, it's just linear. Nonlinear is completely general, but maybe hard to handle, and tensors and polynomials are somewhere in between. It's more sophisticated than linear. You can go as close to nonlinear if you as you want, Taylor series approximation and so on. And many things can be done also in an interesting numerical manner. Let me say a few things that are of general interest. We started with developing new algorithms for optimization of complex variables, not necessarily tensor decompositions. So, for instance, we want to compute a CPD in an optimization framework. We stack all the parameters of this CPD in a vector of unknowns Z, and we optimize over Z to find the decomposition. So it's an optimization problem. And Z could actually be a vector of real variables, X, a real-valued optimization problem, or we could have a complex Z that appears in the expressions as Z and Z bar. Now here we have a problem. With this Frobenius norm, you have Z, both Z and Z bar, and that means that F is not differentiable with respect to Z. There is also Z bar, and there's a problem. Actually, no real valued function in a complex Z is analytic, so cannot be done. So what we do de facto, what everybody does, is you take the real part and the imaginary part of Z, you write out all the expressions, and it's pretty boring and can make errors. And then you optimize over real and imaginary part. And then as a starting point for this work, we realized that you can do it in a different manner, in complex optimization. And that's the following. If you take the real and imaginary part, they are related to Z and Z bar in this way, with the small known matrix J. What you can now do is, instead of computing the derivative, the derivative with respect to ZR, that's the real and imaginary part, you could also compute the following derivative. You compute the derivative with respect to Z, taking Z bar constant, and the other way around. I call this df Z complex. That's called a Wertinger derivative. Has received little attention in signal processing. It's a Wertinger derivative. So you don't have to write out all these real parts, imaginary parts. You do it like this, and it works. It's very simple. Why? Typically, these optimization methods, they make, for instance, a second-order model of your cost function. Here you see Taylor series with the real unknown, real and imaginary part. Now you plug in this G matrix in this way, and then you can combine, and you get this. You can also define a complex Taylor series with these Wertinger derivatives, and then it's convenient. And you can do the whole optimization in that framework. And that's actually the first step of the derivation of our numerical algorithms. We have been developing, we have rewritten the classical optimization routines like quasi-Newton and nonlinear least squares and Lieven-Markar and all this stuff in that framework. And it's very convenient, so you can download it for free for academic research. And then we come to tensor decompositions. This is CPD. This is what we want to do. So it has this form. T is the tensor that is given. We have some multilinear expression of the unknown parameter Z. In this case, is a canonical polyadic decomposition. And we have made it more general than that. Actually, we take any multilinear expression of a parameter vector, not necessarily a decomposition. For instance, for the people who attended the tutorial by Georgios Giannakis on Sunday, he used in his computations, he had a rank 1 matrix V times V transpose. And it was the V that he wanted to know, and he replaced that by capital V, and then afterwards take rank 1 approximation. You can just have V transpose. It's quadratic, and it appears here. And then you have the square for the Frobenius norm. It will be degree 4, and it fits in this framework. Other stuff, constant modulus, channel equalization, same thing. You have the equalizer, and with the modulus squared, and you have a quadratic thing here, and then so it fits in that framework. And we have been developing algorithms that are general for that kind of stuff, or for tensor decompositions, canonical polyadic, block term decompositions, coupled decompositions, and so on. And actually, there is room for improvement. The workhorse algorithm for this is alternating least squares. So it nicely exploits the multilinearity in the following way. How do you find the solution? You keep B and C constant, then you have just A in a linear way. It's with least squares, a linear least squares problem. You solve it. And then you update B, and then you update C, and then A again. Alternating least squares, very simple, takes the structure into account in a very neat manner. But maybe there are other techniques that take this structure also into account in a neat manner and that work better. This is an example. This is ALS for this example. And this is one of the new algorithms. You see here, ALS has linear convergence rate. See a linear increase of the accuracy. This has quadratic or close to quadratic. And this is also something that happens for a difficult problem. ALS is often very good, but it can be slow if the problem is a bit difficult. I'm not saying that this will always do the job in a nice manner, but at least we have been taking into account numerical properties in a neat manner. The approach is as follows. We want to work like in Newton. Newton is your new update. P is the Hessian inverse, and here you have the gradient. And then you are in the setting of numerical linear numerical optimization. You have proven convergence to local optima. ALS does not necessarily converge. This one will converge. You can work with trust regions, line search, etc. But for tensor decompositions, if we want to compute this Hessian and gradient, it's going to be too much work. So we will rather work with an approximation of H. Quasi-Newton or nonlinear least squares. Let's continue with nonlinear least squares. Here you have the Jacobian. Calligraphic F here was tensor minus CPD or whatever structure that you have built. So the number of entries here, this is an object of, for instance, third order. It can be big. So this Gramian, one dimension is all the parameters in Z, and the other direction is all the entries in the tensor. So this is really big. People did that in the past, but it worked well, but it's computationally expensive if you do it like that. So what we did was we really exploit the structure of this CPD. We took into account that you have a rank 1 structure everywhere. So we are never going to construct that big Jacobian. We are only going to stack in memory the factor matrices and a few auxiliary things. We are not going to solve this equation. It's numerical optimization, so there are schemes. You don't solve sets of equations but in an exact manner, but you do it iteratively. It's an approximation. You use preconditioning. And all these things together lead to something that works as follows. You update A, B, and C just like in ALS, but you do that simultaneously. So you don't wait to update B with the result of A. You use the old result for A, B, and C at the same time. So you have a kind of parallel alternating least squares, parallel conditional least squares. You get an approximation, and this approximation is iteratively refined at very low cost. And the result is going to be an algorithm that has these nice properties of quasi-Newton nonlinear least squares and everything. It works very efficiently, the same memory cost as ALS, and of course a little bit more work. It starts with ALS, but with a little refinement, and this little refinement is negligible for large tensors. This is then additional benefits. It's almost embarrassingly parallel in alternating least squares. You have to wait it's with cycles. Here you can do everything in parallel, and it works really well with proven convergence to local optima, etc. Going to hurry a little bit. These are new algorithms. This is ALS. This is just if you run it on a number of this vertical axis, if you run it on a number of problems, in which percentage of the cases, which algorithms is the fastest. So you see the blue always beat ALS. This here indicates in how many cases the algorithm did not find the solution, no matter how long you could do the computation. I can explain what happens in between, but this is a more difficult problem. You see ALS is now here, and the other algorithms work fine. And so this made it into a MATLAB toolbox that we called Tensor Lab, with also other stuff, visualization, estimation of rank, and so on. There is one more thing that I would like to briefly explain, and then I'm going to conclude. There is also something, global minimization of bivariate polynomials. What does this have to do with it? This is the multilinear model. This is the given tensor T. You have your parameter vector that you want to estimate, and you look for an update in a certain line. Alpha is the step size. This is the search direction. Now, a nice thing is it's all multilinear. So what does that mean? That means that this alpha is going to appear here, here, here. Then you have this power 2. The computation of the optimal step in any direction can be done by rooting a polynomial of degree 5, in fact, not 6 but 5. So it can be found explicitly the global minimum in any direction. So this is worth investigating, and actually we generalized, that was something that existed in the literature. It's a result by Pierre Common. And we generalized this to optimization over a plane, 2 search directions or 3 parameters. And in all cases, you can find the solution by solving a problem like this. You have 2 polynomials in 2 real unknowns, x and y, and you have to solve this set of equations. Now, I'm going to conclude with a few pictures that show what TensorLab, the power of TensorLab. The other stuff is harder to visualize, but here you will see. So these are the 2 polynomials, and you have to find the intersecting points. And so you can nicely compute. So actually, we even re-implemented MATLAB generalized eigenvalue decomposition for 2 matrices that is underneath. So another thing that you can use this for, and also of general interest, in fact, assume that you have a function in 2 variables. X and Y. It's something with local optima. And now with this, you can guaranteed find all, well, not guaranteed, but it's very likely, it works very well, all the critical points, including the global optimum. Why? You take just a polynomial approximation of this 2-dimensional surface, Taylor series or whatever, derivative with respect to x, derivative with respect to y, you set them both equal to 0, you get this. And so this is what we solve now. So the blue line could be the derivative with respect to x, the red line derivative with respect to y. These are other examples. So these things, of course, it's not linear, it's polynomial. They can become difficult, but we have pretty good software now. These are, again, these performance profiles. I don't have time anymore, but this is, we compared with algorithms from applied mathematics, and this is our algorithm. So the more in this corner, the better. This is for just an average problem. This is for a problem that is a bit more difficult. And you see that the algorithms that there are in the literature do not compete anymore. After the Christmas break, we will release TensorLab version 2, that will have generalizations for coupled matrix tensor factorizations with all kinds of structures, non-negative, orthogonal, constant modulus, whatever. It works with the same numerical algorithms underneath, complex also, and for data that are full or sparse or even with missing entries. And okay, that concludes my talk. So there is definitely advances in the conceptual advances in the algebraic understanding, in the development of what you can do numerically. And these are now, I think, very useful tools for many signal processing applications, data analysis. And one of the messages is it's somewhere between linear and nonlinear. I think it's a very fruitful zone between the two. Thank you. I know very little about these techniques. I know that there are methods under development for probabilistic tensor factorizations where you take into account a priori knowledge about the distributions of factors and whatever, and you can plug that in, but I'm not an expert in those.
In the beginning, you had this factorization into rank R1, R2, R3 terms, right, of the tensor. Is there a relationship? Because for every tensor, of course, the CP decomposition also exists, right, for every tensor. And is there a relationship between this CP decomposition of this tensor and then the factorization into R1, R2, R3 terms?
Not directly. So I go back.
Or in some special cases, maybe.
Where is it?
Obviously, if R1, R2, and R3 are all one, then it's the CP decomposition, but it's the trivial
Yes,
case.
if you have only one term here, it's a Tucker decomposition. So it's, you could say, is there a relationship between Tucker and CPD? In some way there is. You can write the Tucker core in rank so many. But the nice thing is this actually gives a better view of what rank means for tensors. Rank can be number of terms, like in CPD, but if you have only one term, that's a Tucker decomposition. It's a Tucker decomposition. Multilinear rank is also a generalization of rank, row rank, column rank. That's the dimension of that core here. So for many years there was when I attended workshops, there was a controversy. What's the best generalization of rank? It's actually both. You need the number of terms and also the intrinsic dimensionality of the terms. That is what rank becomes.
So, but then you have the question, should you use the truncated, let's say, Tucker decomposition, or like two terms with a reduced rank, or three terms with further reduced rank? So that's then the question, right?
It then depends on your data, of course.
Sure.
Yeah.
Yeah. But how can you make this decision? So how should you evaluate the data to make that decision?
It depends on the application in the sense that, for instance, in wireless communication, the number of terms would be the number of users. And the size will then depend on the complexity of the propagation. Stuff like that.
More comments, questions? Yes, please.
I'm very well. Just a quick question. You mentioned you're going to use Gröbner basis to solve the...
No, it's better than Gröbner.
Okay. So yours...
Gröbner is not... Yeah, you cannot do it for this. So that's why we looked at that to see all possibilities, but it's definitely not an option.
Okay, because you mentioned how, and then you mentioned Gröbner basis. I was confused.
That was just on this. I took a few slides, and the how was what are the existing things, and then we don't do this. Okay.
Something else? Okay, thank you very much again. Alexander, should we start right away with the next session, or?
Oh, thank you.
So yeah, who's chairing the next session? Maybe we start right away. Who's chairing the next?